So far, we've gone through quite a few steps, from the simple moving average to the exponentially weighted moving average to viewing the moving average as a predictive model, and finally adding a trend component. In this lecture, we are going to complete this journey with the full Holt-Winters model. The Holt-Winters model extends the Holt linear trend model by adding a seasonal component. This makes sense, especially for our dataset, because there is a clear seasonal pattern. In fact, for many time series datasets, there is a clear seasonal pattern. Think of something like air conditioner sales. Obviously, more people buy air conditioners in the summer than in the winter. We have all kinds of sales that are seasonal, such as back-to-school sales, Boxing Day sales, and nowadays, Black Friday sales, which I'm sure you're all familiar with. So how does the Holt-Winters model work? The basic idea is that, for the kinds of time series we would like to model, there are generally three components. There is the trend component, which we've seen. There is the seasonal component, which we are just now seeing. And there is the level component, which is sort of the average value around which everything else fluctuates. These three combine together to form the full time series signal. The question is, how do we combine them together? In fact, for the Holt-Winters model, there are two ways of doing this. The first method is called the additive method. For this model, the seasonal component, or the periodic component, is simply added to the trend and the level. So you can imagine a noisy line added to some periodic signal, and this periodic signal, being periodic, does not change over time. The second method is called the multiplicative method. For this model, the seasonal component changes proportional to the level of the time series. This seems like it might be a good fit for our dataset because it seems like the wavy part actually increases in amplitude as the level gets larger and larger. So let's look at the additive method in component form. As usual, I think the best way to understand these models is to pay careful attention to each of these equations. The forecast equation is sort of the centerpiece of the model because it tells you how each of the components combine to give you the full output. So what does the forecast equation look like here? Well, first, let's recognize that 2/3 of this equation we've already seen. This is just Holt's linear trend model. It says that for each step that h increases, the non-seasonal part of the forecast increases by b of t. The new part is the s term, which obviously corresponds to the seasonal component. Now you might find these indices very confusing at first, but we'll go through them slowly so you understand what they mean. First, we need to define this new variable m, which is used to define the period of the seasonal component. Some people refer to this as the frequency, but it's more accurate to think of it as the period. Remember that period refers to the length of time that it takes for a signal to repeat itself. For example, the period of the sine function and the cosine function is 2 pi. Frequency is actually inversely related to the period. In any case, this is one of those variables that must be chosen manually, but in real-world situations, it probably won't be that hard. As an example, if you're looking at sales data over each month, then we might expect the period to be 12, since there are certain events that happen every year which affect sales. Obviously, this will require some domain knowledge, so the data science practitioner, that's you, should apply what you know about the data to choose this value correctly. So now we know what m is. We also know what t and h are, since we've seen them before. T is just the last known time for which we have real observations, and h is the number of steps ahead that we are forecasting. But what is k? Let's ignore this strange formula for now. Intuitively, k is a number chosen, so that we look back the appropriate number of steps in our training data to choose the correct seasonal component. For example, suppose that our data goes up until December 2020, and the frequency of the data is monthly. Suppose that we would like to make a forecast for March 2021. In this case, the training data is from December 2020 and any time before that. To get the seasonal component for the March 2021 forecast, we would like to use the seasonal component for the latest month of March that we know of, which is March 2020. We would not want to have, say, the seasonal component from November 2020, because that's an entirely different month, which includes Black Friday, which definitely includes data we don't care about in March. On the other hand, note that the level L and the trend B both come from time T, the latest measurement. Only the seasonal component looks further back in time to grab the appropriate point over the entire season. If you're mathematically inclined, then we can do an example to make sure that this works. If you are not mathematically inclined, then just understand the intuition, and that's okay. Remember that we're going to be using a library anyway. So let's suppose that we have t equals 36, and our data is monthly, so m equals 12. Suppose that we want to forecast 15 steps into the future, so h is equal to 15. So if 1 refers to January, then 12 refers to December, as does 24 and 36. So our training data is 3 years from January to December, 3 years later. We want to predict 15 months into the future, which is March, but it's the March 1 year after the latest measurement. We know intuitively that the seasonal component should come from t equals 27. Why? Because that's the last known March measurement that we have. In other words, the one that's closest to 36. So let's see if our formula works. We have k equal to the floor of h minus 1 over m plus 1. If we plug in all of our numbers, we get k equal to the floor of 14 over 12 plus 1, which is all equal to 2. Therefore, the time index for s will be 36 plus 15 minus 12 times 2, which is equal to 27. And thus we have confirmed that this strange formula does indeed work. Alright, so now that we understand the forecast equation, the others are pretty simple. Next we have the level equation. This is almost the same as the linear trend model, and you should feel comfort about the fact that it's the same old exponential moving average. The main difference is that we subtract the seasonal component from y. Note that we subtract the previous seasonal component at index t minus m. This makes sense since in our equations, generally y is considered the forecast, so it's always ahead of all the other components. Next we have the trend equation. This one is exactly the same as before. It's an exponential moving average of the trend as measured by the difference in levels. Finally, we have the seasonal equation. This one might seem strange at first, but at least you can recognize that this, again, is an exponential moving average. In front of gamma, we have the new value, and in front of 1 minus gamma, we have the old value. Again, recognize that the old value comes from one period ago rather than one time step ago, so that's why the previous s is indexed by t minus m. For the new value, this makes sense when you consider the forecast. Recall that y is equal to the level plus trend plus seasonal component. Therefore, the seasonal component is y minus the level minus the trend. If you think of it like an equation, you're just moving the level and the trend to the other side to isolate the seasonal part. Alright, so now that you understand the additive model, let's move on to the multiplicative model. Since you already understand how the additive model works, it's not that much effort to understand the multiplicative model. As before, let's start with understanding the forecast equation. Based on the name of the model, I think the forecast equation makes intuitive sense. Instead of adding the seasonal component, we now take the linear part and multiply it by the seasonal component. The general equation at a high level can be thought of as y equals L plus B all times S. For the level update, we now have y divided by s. That makes sense because before, we had y minus s. For the trend equation, there is no change. For the seasonal equation, we have y divided by L plus B. That makes sense because before, we had y minus L plus B. Alright, so as with our previous lectures, now that we understand the theory, we're going to discuss the main parts of the code. So first, we'll need a new class, which is simply called exponential smoothing. This might be a little confusing since one might think of the EWMA as exponential smoothing, but just remember that in this library, we qualify it by saying it's simple exponential smoothing. So not simple exponential smoothing refers to Holt winters. Next, we instantiate our model. In the constructor, we pass in the data, and we also specify whether the trend and seasonal components are additive or multiplicative. We also specify the period, which in our case will be 12 since our data is monthly. Note that in this lecture, we discussed two models where the seasonal component was either additive or multiplicative. In both these cases, the trend was additive. Stats models also gives you the option of making the trend multiplicative if you think that fits your data. So that might apply when your trend curves rather than going in a straight line. The next step is to call the fit function, which does not require any parameters. And as usual, this returns the Holt winters results object, from which we can then obtain the fitted values, as well as call the forecast function.